The big question for this segment is, do planetary systems represent a new level of complexity? And how complex are planetary systems? Planetary systems are interesting in that they may harbour life. To do so, though, they need a long-lived stable orbit in the habitable zone around a star where liquid water is stable. And they need that liquid water to be stable for a long time. Earth has achieved this remarkable stability through a number of feedback mechanisms. The emergence of a stable solar system from the protoplanetary disk involved the gravitational ballet between these embryonic planets. Some were ejected from the solar system, some collided, and some of those that collided actually stuck. Eventually a system emerged where the remaining planets exerted gravitational tugs on each other that balanced out, a gravitational feedback system, and that has been stable for about 4.5 billion years. Earth is remarkable in that it has maintained liquid water on its surface for over 4.4 billion years, and this is the result of a number of feedbacks between the surface and the planetary interior. Earth has, several times, frozen over. Over 600 million years ago, lower levels of volcanic gas input resulted in a weak greenhouse effect, causing the ice sheets to grow. Ice is reflective, resulting in the Earth reflecting more light back into space, which lowered the temperatures further. This caused the ice sheets to grow more, and a runaway icehouse was the result. This global ice age was thwarted by another feedback. With the world covered by ice, there was limited photosynthesis and no weathering of continents. Both these processes normally suck CO2 out of the atmosphere, and without them, carbon dioxide had nowhere to go. Since volcanoes were still pumping out these gases though, like CO2, the greenhouse gas levels in the atmosphere started to rise, eventually leading to melting of the ice sheets. Melting ice made the Earth less reflective, and so the planet absorbed more heat, which melted more ice, until eventually the ice sheets disappeared, and animals appeared in the Cambrian explosion shortly afterwards. The most common type of planetary system observed in the galaxy are hot Jupiter systems, gas giants in extremely close orbits to their stars. These systems are largely hostile to complex life and formed due to the migration of planets inwards early in their history. The solar system possesses evidence of this process in the asteroid belt, which Jupiter crossed at one point in a march towards Earth. This catastrophe was averted for us by an initial condition, the formation of Saturn. Saturn was big enough to influence Jupiter gravitationally and entered into a resonance orbit where the gravitational feedback between the two orbiting bodies creates a stable configuration, putting the brakes on Jupiter's inward migration. A further feedback between these bodies and the gas in the disk resulted in them migrating back out to the outer solar system, leaving behind the shattered remnants of the asteroid belt, a failed world, but also a stable inner solar system. Plate tectonics is remarkably important for long-lived habitable planets, acting as a planetary thermostat. It's responsible for most of the volcanoes and thus most of the CO2 and water vapor delivered to the atmosphere from the planet's interior. However, plate tectonics also creates mountains which erode, absorbing CO2 into minerals as they do so. This sediment is then recycled by plates back into the Earth's interior at places like subduction zones. Why Earth has plate tectonics when no other planet in the solar system does is still not clear. The plates themselves are just the surface of a convection system spanning the depth of the mantle. This system is very sensitive to temperature. If the mantle heats up too much, it becomes less viscous and moves faster, rapidly dumping heat from the interior. If it cools too much, the mantle becomes sluggish and cools inefficiently. This gives time for radioactive heating, the main power source for the Earth, to warm the mantle. These feedbacks operate to keep mantle temperatures sensible and the plates moving at regular speeds. Simulations of plate tectonics show this nonlinear system is very dependent on its initial conditions, and a system may evolve down very different paths depending on how it started, a characteristic of chaotic systems. This history dependence is known as hysteresis and may be an important factor in why such similar planets as Earth and Venus have such very different tectonic states today. Ultimately, Earth's long-lived habitability is due to its ability to sequester CO2 out of the atmosphere and store it in the rocks. Today it is life that primarily accomplishes this task, both by photosynthesis, but also critically by marine organisms taking carbonate, the dissolved form of CO2, and making shells. From coral reefs to oceanic ooze and chalk, the bodies of dead organisms constitute an enormous sink of CO2. As a result, the biosphere can be considered a nested system, an additional complex system working in coordination with the planet and affecting its geology and moderating the system to sustain itself. If all of Earth's carbonates now stored in rocks were converted to CO2, Earth's atmosphere would look a lot like Venus. Venus is currently a searing hellhole over 400 degrees Celsius on the surface and over 90 times atmospheric pressure with clouds of sulfuric acid. Its surface is hostile to all known life. Yet there is evidence on Venus that it once had liquid water. The difference may have been that Venus did not have plate tectonics or, as far as we know, did not have life. As a result, it lacked the ability to suck CO2 out of its atmosphere and put it in those surface rocks. The CO2 levels rose, evaporating the oceans. Water is an even more potent greenhouse gas than CO2, and as a result, temperatures on Venus skyrocketed further. The end result is a runaway greenhouse effect, the result of a positive feedback between the climate and volcanic degassing. This is an example of a cascading failure, where a failure in one component, for life or tectonics, resulted in a catastrophe for the entire system.